Hi everyone, and welcome to our first sort of preview video for our Apex PDM. This is specifically aimed at our beta testing group. So there's going to be a lot of assumptions about, your technical knowledge. I'm not going to go into how CAN bus works or anything like that. And we're going to quickly move through everything. Before we get started, I think it's important that the hardware abilities of the product are spoken about. So as you can see, billet case system, super seal connectors on the front here, and a big input lug. We're only supplying it with a small amount of current here, okay? So it's only on a small wire to power the stuff on this rig. And USB-C on the front here for connection, and a row of LEDs, RGB LEDs for status. In terms of our channels, we have 10 25 amp channels, 6 15 amps, and 8 7 amp channels. One of them is braked for a wiper. So that's 24 channels in total. Now, we have capped the current flow for the super seal connectors to 15 amps per pin. But as I say, the drivers we're using are rated up to 25 amps. And in testing here, we put 30 amps through them, no problem whatsoever, not really much heat gain or anything like that. But it's more of a, as we test, as we have more of these on cars in the field, we can start to work out what our true current limits can be. And again, that is part of the beta testing program. All of the outputs are PWMable. They all obviously measure their current. They have fail-safes and everything as you'd expect. Onto inputs, we have 16 analog inputs. They can be used as digital inputs or frequency inputs with software selectable pull-ups or pull-downs or no pull-up at all on each of them. We have multiple 5-volt and sensor ground pins on the unit itself as well, so it's nice and easy to wire up. We have 2 CAN bus channels, CAN 1 and CAN 2. And we have onboard logging with battery backup for a real-time clock, so lots of onboard logging available. We also have a dedicated ignition and accessory sense channels, and these can be used things like keep alive on alarm to flash blinkers or do power windows and things like that. As I've mentioned, USB-C on the front for high-speed comms to the PC. And it's a nice aluminium billet case. And another great feature is you can power it purely from USB for the sake of setup. So we can connect this unit without the main lug being powered or the ignition 12-volt sense line being powered. We can connect it purely through USB and work with it just on the bench like that. We can connect it purely through USB and work with it just on the bench like that. Okay, so jumping over to our software, when we launch our Apex software, and again, a reminder, this is in the alpha stages really, before it comes out to you guys for beta testing, we are presented with our start hub, and it automatically scans all available USB ports, and you can see with the Apex plugged in over here that it has indeed picked up the PDM. And if we double click on it, we go into what we like to call the canvas, the visual canvas. Now, we've tried to do things a little bit different with this PDM. A lot of the PDMs on the market, in fact, almost all of them, require you to add objects and sort of programmatically set them up with logical statements and so on. And it can be confusing for novice users. And also, when you plan your PDM design for your install with a car with those traditional systems, you're typically drawing out a circuit diagram on pen and paper and then working out how to program that into your PDM. We've gone the other way, where you draw the system out on the canvas in real time, and it saves you that step. Okay, so let's just have a little look at our test rig over here. So bring the test rig up. You can see we've got our PDM itself over here. We have some LED headlights, a pretend little cooling fan, a wiper motor with indicator for the park position, some incandescent bulbs for the rear lights. Over here, we've got a little switch panel, which are just wired to some analog inputs. We've got some push buttons, some variable resistors, and some toggle switches. And down here, we have a Blink Marine 6-button CAN keypad. We also have our ignition toggle switch over here, which allows us to turn ignition off and on. And I also have a brake switch down here, so I can actually brake the connection for the left indicator bulb so that we can detect an open circuit and give an example of that. Okay, if we go back to the software, let's start having a look around. So standard mouse interactions, as with any CAD software, you can drag things around, you can zoom in and out. We have a mini map down here, you can move things around. And most systems are probably going to work on one page, which is as shown. And you can also add tabs. If you want a new tab, we'll go into that. We can have different pages of our systems, and we can also have groups of objects as well. But let's go ahead. Let's just do something really simple. Let's just do a push button driving, so a mechanical push button driving a power output. So I'm simply going to right click and add an input. And I'm going to choose a digital input. And we can see at the moment our pin has not been set up here, but let's select a pin. Now I know that our red push button on our rig over here, this button here, is on input 8. So let's go down here and choose input 8. Let's give it a name, make it a bit more user friendly. Red button. And the buttons are wired on our rig such that 12 volts goes into them, and then the other side connects to our analog in. So we want this thing to be pulled down to ground when there's no signal. And when we press the button in a momentary sense, and we go above 2.5 volts, it will turn the output on. So let's go ahead and create that button. So there he is. And if I click on this and bring up the real-time data, I can press this button and I can see, there you go, I'm pressing it, then go, pressing it quickly. I can see the real-time values streaming in from this button and also the state of this button. The voltage that I'm seeing, which is capped to 5 volts for analog inputs, but it's safe up to 24 volts. And I can see that the state is going to high. So we've got our input sorted, we've got our system there. How about our output? Well, let's choose the brake lights on our test rig, which I know is on power output 9. So let's add a power output. And again, we're going to choose a power output that matches power output number 9 down here. And again, it's easy to identify which pin it is. You can click up here as well if you need to, so that one there. And we have a little simulation here showing you, the different states that this button is going to go through and what it's going to do. We've set a fuse current to 15 amps. We've set it to be trigger driven. So it will be driven by a trigger that we set. And we're going to turn this accessory mode off. We're going to make it only work when the key is on and the accessory mode is also not on. So let's press create. And there's our power output. So we have it set up here. We have a real-time feed from it. And of course, it's not doing anything because it's not being triggered by this guy. To do so, we're going to simply trigger our state into our trigger. Now, the logic in our PDM, in the Apex PDM, is such that 0 is low or off or false. Anything other than that is considered true. So if this trigger becomes anything other than 0, so it become a 1 when I trigger it, you can see some currents drawn, and on our test rig, our brake lights turn on. And if we let go, it turns off. So a very simple introduction there to our basic input output and linking things up. And it's worth noting as well, you can stack outputs. So if we choose another power output, and I'm going to choose let's choose another one. I think if we go for the little cooling fan, which is on output 14. So we come down here, output 14. I won't rename it now, but I'll create it. And I can link this one also to this. So if I press this button now, we can hear the fan come on, and there we go. Okay, so we've got our brake lights turning on and our fan turning on. And we can again see the live current draw from that little CPU fan is very little. And we can see some various outputs from this, which can obviously be passed onto other objects and nodes. So that's a simple system setting up a push button switch with a power output as a direct connection. Of course, you may wish to use a push button as a toggle. So we'll change that to toggle, and now it will toggle on and toggle off on each press. As you can see here, as I toggle on, the state becomes permanently on, and when I momentarily push the button again, the state turns off. So nice and straightforward on that part. So with these two outputs being triggered by this button, we can see the current draw and so on. It may be the case that we want to diagnose things and see what's going on if there was a fault state. So what I'm going to do is, this thing is clearly drawing about 3.5 amps. When I press the button, I'm actually going to lower this down and set the fuse current to 2 amps. So anything over 2 amps and this output will of course trip. It will retry, see it retrying, and eventually it completely faults out. Now if I look down here, I can see the equivalent of the RGB LEDs that will be on the face of the unit, and I can see that channel 9 has over-faulted. I can see that channel 14 is in use, but it's completely normal, and I can see that these other channels are not used anywhere else in our system. Now, if I were to be looking at this and this diagram is much more complex, or for example, maybe I was on another page, test page, and I was working in this page instead, I may go, well, hang on, I would like to find out, why this is faulted. If I double click on it, it will take me straight to the object. It will locate the object for me. And the same goes up here. If we go to edit and locate object, we can find things. So power output 14, or digital input, red button, double click it, and it will take you to the correct page and zoom in and center on the object itself. So it's a nice, easy way to diagnose outputs and jump straight to them. the next step really, once you've built your entire design, your entire layout, and you may have hundreds and hundreds of objects on here, hundreds of power outputs, different pin listings for inputs, outputs, and so on, we need to think about how we can actually wire our car up. And we've tried to make it as simple as possible. If you click on Generate Setup Sheet up here, the Apex PDM software will automatically create an install sheet for you. It will show you the PDM header, so you've got that to hand. It will show you the fixed wires that you can use for different things. And if you scroll down, it will show you per page what's on there. So on the main page, we can see our outputs, what pin they're on, what we've named them, and in this case, we've left them as default names, the current, a recommended wire size to handle that current, and also the inputs. For example, A18, pin A18 is our red button input. And here it tells us how it's actually being used. It's telling us, look, it needs to be supplied with a voltage to turn on, a voltage greater than 2. And if we change any settings within that red button, this setup sheet will of course change. If we were to change the pin and so on, the information would change. So it's a great way of creating that snapshot of how your system works, how it's wired, which you can then take to the car or to the bench to actually build your wiring loom. So that's a simple setup of digital inputs and some looking at diagnostic. Let's try and do something slightly more complex. Let's do a comparison. Let's also require an analog voltage to be above a certain level before we turn on our power up here. So I'm going to delete this one off and we're just going to use the cooling fan output. And I want it to be that this digital input is on and also our analog input. And on our test rig over here, I'm going to use this top twirly potentiometer here, which is going into a pin on our ECU, on our PDM, sorry, which is going into input 10. And what I'm going to do is, first of all, I'm going to get that information into our system. So add an analog input. It's analog input 10 down here. And I'm going to call this one top pot because that's where it is on our little board. And I'm going to create it. And if I now put all this potentiometer, you can see that I get a current voltage between 0 and 5 volts, as you'd expect, as well as this after transfer function. And the transfer function comes in here. We can set this up to be any type of curve or shape we like. We can also generate sensor curves. We can also import from our sensor database, and we'll be building lots of these in once we finish the actual design of this. But we can put all sorts of stuff in here, and it will then map the input to the output. So the 5 volts now comes in through this transfer function, and you can see it's got this funny step that I put into it. As I smoothly go up or down on voltage, you can see that step that's there, mapping that transfer function. And what I want to do is I only want this output to come on when our analog calibrated number is above 50 and our button is pressed. So we want to come on with 2 conditions when we're looking at an AND gate. Let's drop an AND gate in there, and let's first of all plug him into there. We want it to be when this one is on, and we want it to be when this guy is above a certain level. So we're going to use a level switch for this, and we're going to say value greater than 50, and we're going to plug this one into here. So you can see at the moment 78 is going in, so of course it's going to be on, and if I come back down below 50, it's going to go off. And if I plug that into my AND gate, that one's working, but we need our button pressed as well. So with him on and our button pressed, we can see how our simple AND gate works and our output works. So a nice simple bit of logic building there. Nothing too complex, but it does bring into the system the idea of analog inputs and the idea of logic inputs as well, and logic gates that we can use. We will be covering logic gates a little bit later. We have a lot more complexity and power in our logic and maths builders, but this is just a very basic sort of introduction to show you what's going on. And we can pop everything out again as well, just so we can monitor stuff, bring our voltage up, and there we go. There's our current spike on our 15 amp channel. It's not drawing much current to drive that little fan, but it is working absolutely fine. So next up, what we're going to look at is some of the modules that are built into the PDM. Now you can, of course, using basic building blocks such as timers, hysteresis, level switches, state decoders, PID functions, transfer functions, multiplexers, which let you choose different sources and so on, create any complex logic you can think of. But we also think it's important that some of the more rudimentary systems that are used in the automotive world are built into all-in-one encompassing modules, things like wipers, lighting, blinkers, and so on. Now, before we go any further, I'm actually going to load in a file that we've already made for this test, which is a lighting circuit. I'm not going to save what we've got here, and we're going to load in our lighting module. It's all loaded in, and if we click across to this lighting tab, we can now see we have everything set up for lighting. Now, I've got my toggle switches named top toggle and bottom toggle. So if I turn on my top toggle, I can see one going into side light mode. Side lights are coming on. If I put the second one on, I can see dip beams coming on. But I don't have any more buttons left. And I might be in a car that doesn't have, a 9-way indicator stalk. I might only want to use a singular push button to control all of my lighting. So how do we do that? Well, I have the red button again up here on this digital input, and you can see as I toggle the button, it spikes. And on our lighting module, we have what we call a single button trigger. And if I connect this guy to single button trigger and press it once, side lights come on. I press it again, we get our dipped, and then any short press will simply cycle between dipped and main. Now, we have LED bulbs on, so we're allowing both dipped and main bulbs to come on at the same time, but it may be that you don't want that to happen, and you can turn that off in here if using sort of incandescent H7 style bulbs. And we also have a pass to flash button, which everybody loves, which will give you that sort of Le Mans feel. I have the other button down here wired to our brake light indication. I'm going to take it actually and trigger, as well as the brake light, I'm going to trigger our fast pass light. And if we're in dipped and we press it, we get our 7 quick flashes. I know they're not showing us even on the camera, but they are showing us even in real life. And obviously you can see the brake light also just coming on there because I am triggering it with that quick press. But of course, again, we may even want to go a step further and not actually use any traditional buttons and switches. We may want to instead use purely a CAN bus keypad to do all of the hard work for us. So we can get rid of all of this sort of traditional wiring and simply power ground and 2 wires up to our PDM, and we can have a multitude of buttons and functionality from one Blink Marine keypad. So let's have a quick look at how we might do that. So the first thing to be aware of is a Blink Marine keypad will traditionally come set at quite a slow baud rate, 125 kilobits, and it will be set with an ID of 15. And we have within our software here a Blink Marine programmer. You don't need to get out a CAN sniffer or a CAN tool. You can simply run this tool to configure your Blink Marine panel for an address and a speed. And in the beta units, and probably going forward in all of our units, we're going to set CAN bus 2 to the default for a Blink Marine panel. So CAN 2, you can simply connect your Blink Marine and carry on without having to change anything. But in this case, it's on CAN bus 1, and I've already set it to 500 kilobits. So we're going to go ahead and use it. Let's go into our keypad settings. So we don't have any keypads at present. Let's bring this back up here. We don't have any keypads at present. And what we're going to do is we're going to add one. So let's press add, and we're going to give the keypad a name. Let's call it driver. And we can have as many keypads as you like, as long as they all have different addresses. It really doesn't matter. We're going to match what we've got physically, which is this guy. And we're going to call this first button lights to make it nice and easy. We're going to leave it as momentary, and we're going to leave it that when it's in state 0, it's in the off state, which on the more basic Blink Marine panels means it shows the background color, the backlight color. And when it's in state 1, pressed, it's going to show green. We do have latching and different states as well, but we're going to leave this one in momentary for now, and we're going to press finish. So that then builds our keypad into our PDM, and I'm going to break this connection here, move this guy out of the way, and instead trigger the single button trigger with a keypad button. So if I right click and go to CAN related, choose a button, I can choose the keypad, which is the only one I've got is the driver one, choose the button. I want this to happen in state 1 and press OK, and I've added the button object. And if I blow that up in the real-time view, I can press the button, I can see the output as I hit the button here, and I can see what it's doing. And by simply firing that into our single button trigger, we get the exact same stuff you saw before. Hold it down, and it will cycle all the way back through to turn our lights all the way off. Okay, so that's simply using a CAN keypad trigger to drive our lighting module. Now, the next step really from here is to utilize the CAN keypad properly. On the keypad itself, we obviously have these lights, and you saw the mode was set so when it was pressed, it would go green, and you can see that here. I press it and it goes green. If I hold it down, obviously it turns off. Short press brings everything on as discussed. But let's just shut everything down all the way back through, some long presses and so on. But we may as well use this guy as a telltale. We may as well change these colors based on the mode that the lights are in. So let's have a look at how we can do that. So let's go back into our keypad, manage our keypads, and I'll bring up the big screen again. And let's configure this driver keypad. Now, I'm actually going to use an external source for the LED feedback. And by turning that on, I can say what I want to happen based on different things. And I am going to, first of all, set this guy to go green whenever our lighting module is sending out a signal on our dipped lights. I'm just using the left dip there. And I'm going to make this guy turn blue whenever our lighting module sends out a signal on the main beam. And I'm going to choose the right main beam. That one. And when the lights are in side lights or off, they're just going to show the background color, which we can play with that. We can change the colors. Perhaps we might use pink to represent off or so on, but let's leave it alone like that. Press finish and close that. Now, if we look at our test rig, if we press the button once, we're in side lights, which leaves it in the backlight. If we press it again, it's going to go green because it's showing this output. So on here, we can see that the side light output is in a 1 state, is on, and as a result, that button is picking that up. And if we press again, indeed, it goes blue because it's now looking at the output from the left main. You can see that's now a 1. And if we hold it down, we'll obviously go back to green and hold it down again, back to side lights, which goes back to amber, and then hold it down again and it turns off. And we might want to set that to be completely off when we shut down, or so it's entirely up to you. So that's a good way of using simple telltales. But there's something else we can do as well. We can actually indicate if there's a fault with our lights. So obviously on our PDM body, we're going to get a red lamp. But if we haven't got a red light on our RGB lights, but it'd be nice if from the driver position on that particular circuit that we're trying to control, we can see that there's a failure with our light. So how do we go about doing that? Well, the first thing to notice is in our CAN keypads, we have this last option down here. And if I turn that off, you can see that's what we call our fault indicator. And we can set a source for this. Now, I'm only going to do it off of the two of the main beams down here. So let's do it on the main beam. Let's go and add an OR gate here. There we go. And the error state 0 is normal. So if the bulb is behaving perfectly fine, it will always be 0. If there's ever a fault with the bulb, this will change to something other than 0, usually 1, 2, 3, depending on the different state that it's in. But let's go ahead and wire that one into there and this error state into here as well. So we're now looking at either of these being in an error state. And in fact, whilst I'm here, I'm going to show you how I would add another one. So this guy here, I might do these two as well. If either of these are in an error state, it will pass through. And I'll finally add another logic gate here to show if either of these are in an error state. So if any of these 4 are in an error state, this output will become true. Now, if I try and find this OR gate, it's going to be called OR gate. It's quite hard to locate. So instead, I'm actually going to add just a simple connector. And I'm going to call this light error. There we go. And it's just a placeholder. It's a pass-through variable we can use to link things up. But it's also a nice way of labeling nets or connections within your system. This one's called light error. I've named it light error, and you can see that down there. Now, what I'm going to do is drop back into our keypads, configure, and I'm going to set this guy to be on that connector's output. So if that light error output becomes true at any point, then what will happen is the light error will turn on and our button will indicate as such as an error. And what I'm going to do is I'm going to make our main left bulb have a minimum current of 6.5 amps, and a maximum current of 10 actually, maybe make that 9 amps. Now I know, actually no, it's not going to do it, it's a 6.5 amp output. There we go. Now I know that this isn't going to draw 6.5 amps. So this guy is going to pick up and think, hang on, there's something wrong with this bulb. So let's go ahead and press the button. We're on dipped. We're on, dipped now. And we're going to go to main. There we go. An undercurrent fault has occurred. It's passed through, it's passed through, it's passed through, it's passed through. Light error will be on. And if we switch to look at the rig, you can see, it's quite hard to see, but that is actually flashing red alternately between red and orange to indicate that your lighting circuit has an issue. And if I clear that, I just change the current back on this guy to 0.5 amps minimum current, and you can see that the error cleared and it correctly indicates that the bulb is now back on its normal full beam indication. So the error is gone and we can see that everything is now passing through as false. So light error has now turned off. Next up, just a quick look at the mostly used blinker module. This guy, again, we've tried to add some features to it to make it a little bit more user-friendly. If we double click on it, we can go into it and we can set up its on time and its off time. And we also have something called fast on fault. So this is designed to work like those traditional blinker circuits, where if you have a singular bulb fail on your network of bulbs, because you usually have one channel driving, for example, the entire left-hand side indicator system, you want the bulbs to flash twice as quick. And this is exactly what this does. You set the minimum current you expect that network to run. And in this system, when it runs at about 1.5 amps. If a bulb drops, it's going to drop below 1 amp. So I've set the minimum current to 1. And all you do then is tie the current, the amps, back into the input, which is what's happened there. The left trigger, I'm going to go ahead. I'm actually going to break this connection. Oh, actually, no, I'll use the red button here. So let's just check it. There we go. The red button's working fine. I'll put that on there like that. And I'll connect this into our left trigger. Now, if I press this, you will see our indicators work standard sort of rate. Actually, I'll make this really obvious. I'll make this 1 second off and on, and then go again. Okay, and we can see that actually the current isn't going above 1 amp when the bulb is on. So it's actually thinking that it's already in a fast on fault state. So we will change that to be a little bit more sensitive and change it down to 0.5 amps. So it should now, with that bulb on, be flashing at the normal rate. There we go, 1 second on, 1 second off, as expected. But as I mentioned before, on my test rig here, I do have a button down here which I can turn off to break that left-hand bulb to open that circuit. So I'm going to press that button there and turn that off. And now if I run the button, you will see they flash twice as quick because it's picking up that broken circuit. That bottom bulb isn't flashing. And if I turn that bulb back on because I fixed him, it picks it up and it continues to work as expected. So it's a very quick and easy way to diagnose, in real time as a driver without wasting fault indications or keypad buttons or anything else. You can just tell that one of your indicator bulbs has gone pop. Of course, at the moment we are on our lighting page up here. If I go back to our big picture, we are on our lighting tab. And it may be that on our system page, we want to know what the current is of the side right. Perhaps we're building another circuit that does something with side right, and we need to make a link to that output. Now, in the Apex PDM, we use that by calling something called a variable. We create a new variable, and we can choose anything within our system to pick up. So we're going to pick up that power output, I think I said our left side light, and its current. And if I do that, I can see here in real time, the output is auto scaling, so it will move up and down as it tries to find its level. But I can scale in and cycle through those bulbs and turn them all the way off. There we go. Okay, so I can now see exactly what's going on. There's the bulb on, and there's the bulb warming up and cooling down a little bit and giving you a bit of an offset there. But we can see the input from that bulb, from that side light. And if I turn him off by holding down, again, we can see that current will completely disappear and it drops to 0. So that's the basics of analog and digital inputs. We also have frequency inputs as well, which we can add in the usual manner. But of course, there may be times when we need to receive information from our vehicle's CAN bus. And to do that, we use a CAN bus input. So let's go to the CAN bus menu and manage our CAN inputs. In here, we can choose to add some messages. We can also simply import a DBC file. If you have a DBC file for your particular ECU that you're using or your OEM CAN stream, you can bring a DBC and populate this entirely. But what we're going to do actually is just create one at random. And I know I'm going to make this up, that at address 400 on CAN bus 1, we have this byte field, and I am going to say that this block of data here is the engine's cool, giving it a name. And if I click on it, I can set up the bit lengths, the multipliers, the offsets, and so on, and also a fallback value. So if this message doesn't come in for 5 seconds, it will fall back to 0. You might want it to fall back to 120 degrees. So if we don't receive an engine coolant temperature, we assume it's overheating and we begin to fire our fans off. But ultimately, this lets you the full flexibility here to set up our CAN bus input streams. I might add another one here. Let's pretend that this one is the TPS position. Again, it might be more than that. It might be across might be across here, and that might be engine RPM, for example. But all of these we can set up, and if we press save and close, we can then bring those CAN variables into our canvas. And we simply do that by right-clicking, CAN related, add a CAN input, and then choosing the variable that we've added. So this is on message 400, and we want the RPM, press OK, and there's the CAN variable. Now, we don't have an ECU connected to this, but if we did, we would be seeing a real-time value here of what's being decoded at that address in real time. And we can then feed this into other things, maybe a level shifter or a math function. Maybe we want to add it to something else. You know, all these different options we have here to play around with it. Maybe we want to add it to a constant. So we can add a constant, and maybe we want to add it to the number 45. And we can plug that in, and we can see that 45 add 0 is 45. But the fact is, we can really build complexity by capturing CAN inputs from other systems, such as I say, ECUs, OEM streams, data loggers, all sorts of options there. Any sort of aftermarket CAN bus transmission system is compatible with our PDM. Following on from CAN inputs, it may also be useful for us to broadcast onto CAN bus something that's happening within our PDM. For example, we may have a dashboard, a digital dash with CAN bus input that has a certain position within its fields that we can use for a telltale. Maybe we set up a high beam indicator on our dash. So let's have a look at how we would achieve that. So we go up to our CAN bus menu again, manage our CAN outputs. And we've already been playing with this, I've already got one set up there. But let's assume that at address 555, this bit here is the high beam indicator, okay? You know, you can name it whatever you like, but we are going to transmit this variable, and we're going to transmit it once a second. We could transmit it based on an event, based on a trigger happening. Maybe they've pressed a button or something like that. But we're going to transmit every second this entire frame. And we could just transmit a fixed value. So we could, for example, if we had an ABS controller that expected to receive the number 106, we could put it in here, ABS hack maybe, and we could set this guy to, you know, 106 or whatever we need it to be, and it will transmit out 106 every time. So the system every second will transmit 106 here. But on this high beam one, click and drag there, on the high beam one, we want to transmit the value of the lighting system. Is the lighting circuit on or off on the high beam? So let's go ahead and pick him, go to set, go to lighting, and we can just do the left main. And when that left main output of lighting is true, is a 1, it will transmit a 1 on this bit. And if we set our dashboard up correspondingly to receive that, we can, of course, turn that off and on our dashboard. Likewise, maybe we just want to transmit the current for one of our outputs. So we could say, you know, the brake light current on here, and we can say the way it's going to be sent, little endian, signed, an offset and a multiplier, and we're going to choose our power output, which is our brake lights and his current. So now, out of byte 4 of message 555, we will be streaming the current the number directly as a little endian signed number with no offset or multiplier. So there we go. So there's our CAN outputs. And there's nothing to configure in here because the CAN outputs are picking from the canvas and transmitting. There's no connections to be made within the canvas itself for CAN outputs. Moving on, we do have quite a lot of complexity within this system to build our own maths and logic functions. And certainly more advanced users are going to start using these sort of features to do things. The maths and logic builder are particularly powerful. They're quite easy to use, and we'll go through and we'll have a little play with one right now. So let's create a new logic block. Rather than just a simple and, or not gate, we can add those all day long. Let's create our own logic block. So add logic block. Now on the left here are the input variables, and imagine these as the sort of inputs to the node. So I'm going to create a logic block that if the RPM is bigger than 500 and a button is pressed, it's going to come out as true. So I'm going to make this one called RPM input. Add a first variable called RPM input, and I'm going to have a second one called my button. There we go. So we have said that when the RPM is larger than 500, there we go. We can delete that one off. And the button is true. We output as true. Now, we've just made this circuit up right here, but we need to test this because we might have this comparison around the wrong way. And we have an inbuilt testing system within the logic builders and the maths builders, and it's called test evaluate. So let's put a number in for RPM input. Let's put 600 in, and the button can be on. And let's have a look. We get false. And that's because if we look at what we actually tested, we tested was 500 larger than RPM input. So it was the wrong way around. So we can see this, and we can delete these connections by clicking off there and dragging him around that way, because that's actually what we need to test. Let's test it now. RPM 700, the button's pressed, and we get true. Let's test RPM 700, but the button's not pressed. We get false. So we can see how our system's going to work. And once we're happy with our logic, we can press OK, save, give it a name. I'm going to call it RPM logic, doesn't matter. Press OK, and we've built our logic block. And we can then feed things into this. RPM input had to be over 500, so let's make this one 600, this constant. We're going to steal him. Actually, I might feed it from this guy. The output of here being 600 into our RPM input. And our button, I'm going to use that CAN keypad button. I'm going to use this guy, this button here. He's currently 0. Connect him onto that one. And now when I press this button, which is showing me the one here, and I press it, I see that correctly my 600 is going in, my button is being pressed, and it becomes on. Let's change this constant to maybe a little lower, 200 say, and I press that button again. I can see now that it doesn't work. So very easy to build complex logic. Maths functions are exactly the same. I won't build one, but you can do standard maths operations, drag them around, and it will output the number that it computes. Whereas a logic system will only ever output a 0 or a 1, a true or a false. In the top left here, we've had this guy hanging around, this system object. Now, you can only ever have one system object. You can't delete him. He will always be on the main page, and he is sort of the overall manager of the PDM itself. You can see what's going on with the ignition switch, you can see what's going on with the processor load, the CAN states, the system states, the current and everything else. And you can also, with, for example, a button input, reset any faults on any power outputs, and also hold keep alive. So if you want the system to shut down after a time has elapsed, you could perhaps use a timer module that counts up, and you can trigger it when the ignition turns off. It will continue to run, and you can use that to use the keep alive to perhaps have follow me home headlights and so on. Also, you can pop this open and see some information in real time. You can see the onboard temperature in the 3 different zones of the PDM, the voltage and the current bar as a quick way of seeing what's going on. And in double clicking the system object, we bring up some CAN termination settings and the keep alive time. If you want to cap it so the system could never drain the battery flat because your logic hasn't worked properly. Whilst we're here, a little Thing to note, if you're in any object at all, press help and it will jump you straight to the right page of the manual where it will tell you how everything works. So you can jump in and see exactly what's going on. Now, in terms of monitoring and diagnosing, of course, you do have the inbuilt loggers for all of your inputs and outputs. You can see exactly what the system is doing directly in here in real time. But there are two logging systems on the PDM. We have the onboard logging, which allows different triggering to fire, and it records to SD. That won't be ready in the beta release. The hardware is there, but the software still needs signing off for the beta release for the onboard logging. But what we do have is the inbuilt software logger on the Apex configuration software. If we go to the logger and view logger, it brings it up down here, and we can add things to it. We can add channels to it. So if we right click on digital input 1 and add to logger, we can choose to log the voltage, for example. Let's press OK. And you'll see here it's noisy because it's a voltage input, picking up spikes. And actually, I want to make it not auto scale. I don't like the auto scaling. I'm going to make it scale between 0 and 5 and stay there. And I'm going to make the side light current. Actually, I'm going to measure the brake light. And if we right click on the brake light and add nodes to logger, we can choose to toggle his current on the brake light. Let's press OK on there. Now, if I press the brake light, which is also doing our 7-stage flash because it's triggering up there as well, we can now accurately monitor the current from this particular input, in and out. And I can also pause the logger at any point. I can pause it and I can scroll through it. And I can also add markers. I can add a marker there, I can add a marker there, and it will tell me the differences, the time that's elapsed, and so on. And if I want to manage the groups or delete a channel, I can right click, remove channels, or do it within here. And I can also add anything that's in our system into that group, or make a new group. There we go, and add the error state for that one, or maybe add the retry count as well for there. The side light current as well, I'll add that as well. Perhaps we want to add the button state there and press finish. And we now have this second channel. And if I press resume, I believe it was button 1. Yeah, there you go. Button 1 is now being logged as well. So we can really start to see this logger in action, picking up lots of different things all at once. And again, as I say, we can pause it, we can add markers and so on. So that's the sort of inbuilt logging, multi-channel logger. We can make it bigger if we really are focusing on logging. And also, there's another type of logging, which is more of a diagnostic and reporting logging, where we can file log. And that will log every single variable that the PDM is receiving to a file of choice. And we can use that as part of diagnostics. And as part of the beta testing, I would ask that we receive a log of everything, as well as this information here. This tells us what firmware we were running, the hardware version, everything we need to know. So thanks everyone for joining in this really quick spin through of the new Apex PDM from Motorsport Electronics. The beta program is about to launch, and we are looking for experienced beta engineers, as well as those that are complete novices, to give us that feedback of what they found easy, what they found difficult. I haven't covered the circuit builders that are built inside of the PDM software there, which allows you to very easily create simple circuits like fuel pump controls and so on. That will be an upcoming video. And I do welcome, once the software is available, we'll post again on our website, that everyone downloads the software. It's free, have a play around with it, and we welcome any and all feedback. If you guys have ideas for modules we should have as standard, I know we've been floating the idea of a water pump and cooling fan controller, anything like that, we want to hear about it. We want to make this the best PDM on the market. Price-wise, it's going to be the most affordable per channel PDM made in the UK, made worldwide, we hope, actually. And it really is going to be something that we think is going to change the game for those sort of users that are coming into this PDM world and a little bit put off by the competitors' approach with all this logic programming stuff and drop-down boxes and the things that we just look at and think, this could be done a little bit better. As I say, all feedback welcome. See the comment below. There's a short form there to apply to be an actual physical beta tester, where we will send you a unit to play with and to use and to install. And we very much look forward to hearing from you. Cheers.